Ever stop to think if glitches in a quantum computer could be as fixable as, say, typos in a Word document?
It seems like totally different worlds, doesn't it?
Totally. But it turns out the challenges of keeping digital files intact and, understanding the fuzziness of quantum reality,
Hmm.
they're actually deeply intertwined.
Yeah, this 1996 paper we're looking at reveals this fundamental trade-off. It's about how robustly quantum information can even be stored.
It's wild. Thinking that the super weird world of quantum physics has this deep connection to the, well, very practical realm of making our digital information reliable.
It does sound disparate, but what's fascinating is precisely how deeply connected these areas turn out to be, really at a foundational level.
Exactly. And that's where we're diving in today. Our source material is a, well, pretty groundbreaking 1996 paper from A.M. Steane. It's titled Error Correcting Codes in Quantum Theory.
That's our roadmap.
Right. Think of it as our roadmap for today's intellectual adventure. And for the learner listening in, our mission basically is to uncover this surprising bridge, a bridge between the fundamental laws governing the quantum realm and the technology we use every day to keep information safe.
Prepare for some aha moments, I think.
Definitely. We're linking the truly abstract with something surprisingly familiar.
Absolutely. And just to set the stage, this isn't, some pop sci article. We're wrestling with a physics research letter here
So get ready to engage the brain. Yeah.
in a whole new way.
Okay, let's unpack this then. So, building on the idea that there are fundamental limits to what we can know about the quantum world, like the famous uncertainty principle for position and momentum.
Right, Heisenberg.
Yeah, exactly. This paper introduces a new limit, specifically for information encoded in a discrete quantum system.
Mm-hmm. So not position and speed this time.
No, it's about how well protected information can be when we look at it in two different bases of measurement.
That's right. Imagine trying to describe the orientation of a line, maybe. You could describe it relative to horizontal and vertical axes, right? Or you could choose a different set of axes, maybe tilted ones.
Okay.
These different sets of axes are kind of like the bases for measuring quantum information. They're just different ways of asking the system a question. And this paper considers two specific bases that are mutually rotated. Think of those tilted axes.
Mutually rotated. Okay, I'm picturing two different ways of looking at the same quantum information. So what's uncertain about that? Where's the limit?
It's the robustness of the information itself. Imagine trying to read a message written in two different alphabets that are twisted, relative to each other.
Okay, like a cipher.
Sort of. If the message is crystal clear in one alphabet, making it really resistant to errors in that form, it might be complete gibberish and incredibly susceptible to errors when you try to read it in the other, rotated alphabet.
Okay, that makes sense. So clarity in one comes at the cost of vulnerability in the other.
Exactly.
And the paper spells this out, right? If you can correct a lot of errors when you analyze the information in one quantum basis, you're basically setting yourself up for a lot of errors if you try to analyze it in that mutually rotated basis.
Precisely. The paper gives a clear example.
Yeah.
If multiple error correction is possible in one basis, it's inherently ruled out in the other. It's a fundamental trade-off.
Okay.
And this really sets the stage for understanding why something like the phase relationship in macroscopically different quantum states is so darn fragile.
Which we'll definitely get to. But first, the paper does something really unexpected, doesn't it? It connects this quantum uncertainty to something from the classical world. Error correcting codes. That's the stuff that, keeps our downloads from getting corrupted, right?
Exactly that. Classical error correcting codes, they work by adding extra bits to digital information. Redundancy.
Right.
These extra bits allow us to detect and even correct errors that might creep in during storage or transmission. Think of a simple example, a parity bit.
Yeah, I remember those.
You add an extra bit that makes the total number of ones in a sequence either even or odd. If a single bit flips, you know something's wrong.
Right. It breaks the parity.
Exactly. And more complex codes can pinpoint and fix multiple flipped bits. A key concept here is the Hamming distance.
Hamming distance.
It's simply the number of positions where two code words differ, how different they are. And the minimum distance of a code tells you how many errors it can handle.
So a greater difference between valid code words means more errors can be corrected. Got it. Now, how does this classical stuff connect back to the quantum side?
Okay, here's where it gets really interesting. The paper presents what it calls a remarkable property. It's Theorem 3 in the paper.
Okay.
It states that if a quantum state is a superposition, a mix of words that form a linear code in one basis, and crucially, all the words contribute equally. They have the same coefficient or amplitude in the quantum state.
So they have the same weight or importance in the mix.
Yes, precisely. Equal superposition. Then, when you look at that same quantum state, but in the rotated basis,
Yeah.
the superposition contains words that form the dual of that original code.
Whoa, hold on. The dual code, what's that?
It's like the quantum world has its own built-in translation mechanism for error protection properties between these bases.
Okay, dual code, that sounds important. Unpack that for us.
Right. So think of it this way. If you have a linear code, let's call it C, it's dual code, often written C prime or C perp,
Okay.
is a related code. It's made up of all the words that have a specific relationship with the original code's words. Specifically, if you take any word from the dual code and perform a bitwise AND operation with any word from the original code.
Bitwise AND, like in programming.
Exactly. Then count the number of ones in the result. For any pair of words, one from C and one from its dual C, that result will always have an even number of ones, even parity.
Huh. Okay, so there's this strict mathematical relationship.
Yes. And if the original linear code has certain properties, say length n, k information bits, and a minimum distance d, we denote it as an NKD code. Its dual code will then be an NNKD code. Notice the dimensions swap around n. It has its own minimum distance d.
So n stays the same, but k becomes nk. Interesting.
Think of the original code as defining a specific flavor of information protection. The dual code then represents a complementary flavor. It's almost like the opposite side of the same coin, highlighting different aspects of the information structure and vulnerability when viewed in that rotated basis.
So it's like there's this hidden mirror relationship between how information is encoded in one quantum basis and how it shows up in the rotated one. And that mirror is defined by this concept of dual codes. That's a really unexpected connection.
It is. It's a profound link. And the paper even suggests that linear codes seem to be particularly efficient in how they balance error correction capabilities across these two bases. They seem to get closer to the limits imposed by that error correction uncertainty relation we talked about earlier, compared to nonlinear codes.
Interesting that linear codes seem to have this special property. Now, the paper then moves on to talking about implications for quantum superpositions, even bringing up the famous Schrodinger's cat thought experiment. How does all this code stuff relate to a cat being, both alive and dead?
Well, the paper considers a specific quantum state in basis 1. It's a superposition of the state with all zeros and the state with all ones. Basically, thou 0.0 plus EIV 11.1. That was a relative phase.
Okay, the classic cat state analog.
Exactly. Now, using Theorem 1 and the corollary to Theorem 2 for the paper, they show what happens when you look at this state in basis 2, the rotated basis. If that phase is 0,
Yeah.
then in basis 2, the state becomes a superposition of all the words with an even number of ones, even parity words.
Okay, and if the phase is different?
If it's pi, meaning the second part has a minus sign relative to the first, then in basis 2, it becomes a superposition of all words with an odd number of ones, odd parity words.
So even parity versus odd parity in basis 2, depending on that phase in basis 1. These are indeed macroscopically different situations in a sense, like alive versus dead.
Right. Very distinct possibilities existing in superposition. But the paper also highlights how incredibly fragile that phase information is.
How so?
Well, to experimentally tell the difference between phi being 0 or pi, you'd need to measure the state in basis 2 and figure out if it has overall even or odd parity, right?
Makes sense.
But here's a rub. Even a single bit flip, just one tiny error in basis 2, is enough to potentially flip an even parity word to an odd parity one, or vice versa. It completely destroys your ability to reliably determine the original phase.
Wow, just one error.
Just one. The paper gives a really stark example. If you have n,001 bits,
Like,
quite a few, and a seemingly small error rate, maybe 2% per bit,
seems manageable.
you'd think.
Yeah.
But the probability of having no errors at all across all 1001 bits, which is what you need to be sure about the overall parity and thus the phase, it plummets to something like 10 to the power of negative 29.
10 to the minus 29, that's basically 0.
It's astronomically small. It just highlights the immense challenge of actually observing quantum interference effects in these kinds of macroscopic superpositions. So yeah, the quantum cat might be in a superposition, but actually seeing the interference pattern between its alive and dead aspects is practically impossible because it's so hypersensitive to errors.
It is a significant hurdle, a huge one. But the paper doesn't just leave us there, does it? It offers a more optimistic outlook. It actually proposes a way to find quantum states where error correction is possible in both bases simultaneously.
Well, possible in a specific, clever way. It sounds like it might offer a way around that fragility.
Error correction in both bases. How does that work with the uncertainty thing?
It's not about breaking that fundamental uncertainty relation we started with, but finding a way to kind of navigate it strategically. The paper lays out the conditions needed for this.
Okay, what are they?
So imagine you have two encoded quantum states. Let's call them Emin and Shab. In basis 1, the Hamming distance between them needs to be greater than 2. They need to be sufficiently different in that basis.
Okay, condition 1.
Then you look at their superpositions in basis 2, specifically the sum of plus Sheb, let's call this Shak, and the difference Sheb, call it Sheb. The Hamming distance between these two superposition states, when viewed in basis 2, also needs to be greater than 2.
Huh. So we need distinguishability between the original states in basis 1 and distinguishability between their sum and difference in basis 2.
Exactly. We need a certain level of difference, a certain error robustness in both bases simultaneously, both for the individual states and for these specific superpositions that encode the phase relationship, the plus or minus sign.
So we need these quantum states to be sufficiently different from each other in both ways of looking at them. How do they actually construct such states? Do they give an example?
They do. They use a specific well-known classical code, the 734 simplex code.
Okay, what does that mean again? 734.
Right, it means it uses 7 bits total, N7. It encodes 3 actual information bits, K3, and its minimum Hamming distance between any two valid code words is 4,
Huh.
D4.
D4 is pretty good for error correction.
It is, and this code has a neat property. It can be augmented slightly to create a related code with minimum distance 3, and importantly, its dual code, which turns out to be the 743 Hamming code, also has a minimum distance of 3.
Okay, so they're leveraging these well-studied classical codes with good distance properties, and importantly, their duals also have good distance properties. How do they build their quantum states, the Che and Cheb, from this?
They construct reb as superpositions of words that form non-overlapping subsets of that distance. 3 augmented simplex code in basis 1.
Non-overlapping, meaning no code word is in both Che and Feb.
Correct. Because
Oh.
they are non-overlapping and come from a code with distance 3, the Hamming distance between the states A and pub in basis 1 is guaranteed to be at least 3. So that satisfies our first condition, distance 2.
Okay, makes sense. What about basis 2?
Then when you look at their superpositions in basis 2, remember soc is the sum and fet is the difference.
Yeah.
It turns out cac plus pipib ends up containing just the even parity words of that dual 743 Hamming code. And pib contains just the odd parity words of the same dual code.
Ah, so the sum difference maps neatly onto the even mod parts of the dual code.
Exactly. And since these are also non-overlapping subsets of a code that also has distance 3, the Hamming code, the distance between puk and pib in basis 2 is also at least 3.
Condition 2 met. That's pretty ingenious.
It really is.
So by carefully choosing these quantum states based on the properties of classical error correcting codes and their duals, they managed to get a degree of error correction, a minimum distance of 3 in both ways of looking at the quantum information.
Right.
It's like finding a clever way to write our message that's resistant to both types of twisting or error types we talked about earlier.
Precisely. This means we can encode both the fundamental quantum bits themselves robustly in basis 1, distinguishing Cepher from Sheb, and also the delicate signs, the phase information captured by the sum, versus the difference robustly in basis 2, distinguishing Cepher from Pred.
And that opens up the possibility of creating and observing interference in larger, more macroscopic superpositions, doesn't it?
That's the really exciting prospect here.
Which brings us back to Schrodinger's cat. Maybe not literally, but the idea. The paper suggests this approach could pave the way for actually seeing interference in these kinds of large superposition states, right? Because we can protect that crucial phase information.
That's the hope, yes. The paper sort of redefines what it means for two states to be macroscopically different. It shifts the focus away from just, say, the average value of some property.
Like average position or something.
Right. Instead, it focuses on the number of errors the Hamming distance needed to confuse one state with another, how robustly distinguishable they are.
Okay, a more information theoretic view of macroscopic difference.
Exactly. And they work through an example using this idea. They consider NT5000 bits, much larger now, and aim for a desired Hamming distance of D1 1001 in basis 1.
Big numbers.
Huge. And based on their error correction uncertainty relation, this suggests an implied minimum distance in basis 2, D2, of around 1213.
Okay.
They then explain how, by using specific constructions, subcodes of augmented dual linear codes they could achieve. For instance, D1 1002 and D2 greater than or equal to 241.
Still pretty large distances.
Yes, and with these distances, you can create superpositions, like sub plus reb, where you can experimentally determine the sign of the interference, that plus or minus, with a reasonably high probability. In their example with that same 2% error rate per bit we discussed earlier.
The one that was disastrous for the simple cat state.
Right. For this encoded state, the probability of correctly determining the sign and thus observing the interference is around 98%.
Wow, from 1029 to 0.98. That's monumental.
It's a monumental improvement. Because now, to mistakenly get the sign wrong, you'd need at least D212 errors to occur in basis 2. With D2 241, that's about 120 errors needed to flip the outcome.
Much, much less likely than a single error causing problems.
Far less likely, even with a 2% error rate over 5,000 bits. So, by using these clever encoding tricks rooted in classical error correction and dual codes, they're essentially making those fragile quantum superpositions much more resilient to the kind of noise that would normally just wash out their quantum nature.
Okay, that really clarifies the potential power of this approach. They do add some caveats, though, right?
Yes, precisely. They acknowledge that, in the real world, error rates might increase as n gets larger, and the assumption that bit errors are completely independent might not always hold perfectly.
Practical challenges.
Practical challenges, definitely. But the paper indicates that there are conditions, reasonable conditions, under which the core argument still holds.
Okay. So, bringing it all together then, what are the big takeaways from this deep dive into Steane's 1996 paper? Feels like we covered a lot of ground.
We did. I think the first major point is this fundamental link it reveals between, well, quantum theory and the very practical field of classical error correction.
Yeah, viewing a quantum system as an information-bearing thing with limits.
Exactly, with inherent limits on how robustly that information can be stored when looked at from different quantum perspectives. That's the new uncertainty relation.
And then perhaps the most surprising bit for me was that powerful connection between quantum states built from linear codes in one basis and their dual codes appearing in the rotated basis.
Absolutely central. And this connection has really significant implications, especially when we think about those delicate quantum superpositions like the cat states and the huge challenges in observing their interference.
Right. The paper highlights that extreme fragility of the phase information in the simple all zeros plus all ones state.
Making interference observation practically impossible there.
But then it offers this potential path forward. By using error correction strategies inspired by classical coding theory, specifically using codes and their duals with good distance properties.
It suggests a method for achieving a degree of error correction in multiple quantum bases simultaneously, protecting both the state itself and its relative phase.
And that opens the exciting possibility, at least theoretically, of creating and observing interference in significantly larger, more macroscopic quantum systems than previously thought possible.
It really does. Now, the experimental realization of these highly controlled, encoded quantum states, that remains a formidable challenge, no doubt about it. But this work laid crucial theoretical groundwork.
And you mentioned a note added later.
Yeah, a note added in proof mentions related work appearing around the same time and points towards the generalization of this coding method for handling more general types of quantum communication errors, not just bit flips. So the ideas were clearly expanding rapidly.
It's just amazing to see how these seemingly separate fields, the abstract world of quantum foundations and the very applied science of information theory and coding, are so deeply intertwined.
It really is.
It makes you wonder what other unexpected connections are just waiting to be discovered when we really delve deeper into the fundamentals.
Indeed. This deep dive really underscores how thinking about quantum systems through the lens of information, noise, and error correction can unlock totally new possibilities and provide a fresh perspective on fundamental quantum phenomena. It's not just about computation. It changes how we think about the quantum world itself.
Okay, the learner, let's wrap this up with a final thought, something to mull over. Consider how this interplay we've discussed between the abstract quantum rules and the practicalities of information encoding might drive future technological advancements. Not just in quantum computing, obviously, but maybe even in our fundamental understanding of what information is at its deepest level. What other seemingly unrelated fields might hold similar hidden connections, similar dualities perhaps, if we just look closely enough?
A great question to ponder.
Thanks for joining us on this deep dive into quantum error correction.